Hi class, here's our lesson on moles. So up until this point we've been talking a lot about what atoms are, what do they do, how do they bond. We've been talking about how electrons are either lost or gained or shared in order for them to become more stable. We start talking about reactions, about how combustion and acid base and double displacement works. And now we're going to be talking about quantifying those things. So let's talk about how we can quantify things. So how much of something do we have? How many pencils do we have in a box? Well, we can just count those pencils. How many paper clips on the desk? Depends on how many paper clips there are, but we could count those. How many hairs on your head? Well, that's a little bit tougher. It would probably take a long time to figure out how many hairs there were on your head. How many drops of water in a glass of water? Well, that would be super tedious. How do I get individual drops out of a glass, and how long would that take to count them all? How many atoms of silicon are there in a glass full of sand? So not only would we have to count every individual grain of sand, but then we'd have to figure out which part of silicon dioxide, which is what sand is, are silicon. That's pretty tough. So let's talk about different ways of measuring things. So counting, as we can see, will be good for some things, but then it'll have its limitations. We can use percentages, and we can count by mass. So when we count, you can count by ones, by twos, by threes, by fives, tens, hundreds, thousands, millions. Here are a couple of usual ways that we count. We can count 2, which would be a couple. We can count 3, which would be a trio. We can count 12, which would be a dozen. And it goes on and on like that. So when we count atoms, when we count in chemistry, we're talking about things that are incredibly small. Atoms, ions, molecules. And so in order to have a measurable amount, we have to count a lot of them. If you'll remember, one hydrogen atom, which is just a proton, weighs something like 1 times 10 to the negative 27th kilograms, or 1 times 10 to the negative 24th grams. It's a really small number. And so in order to have a measurable amount, a non-negligible amount of stuff, we have to have a lot of it. And when we talk about having stuff, we're going to talk about particles. Particles is a kind of catch-all term. It could mean atoms, it could mean ions, molecules, or formula units. And down here we have some examples. So an atom would be something like silver, or anything else that you find on the periodic table. Iron, or copper, or lithium, anything that you can find on the periodic table. You can have an ion, which is the atoms on the periodic table with a charge. So it can either be plus or minus, but it has to have some charge. We can have a molecule. A molecule is a compound held together by a covalent bond. So sulfur dioxide, water would count as a covalent molecule. You could have something like carbon dioxide. All those things are nonmetals bonded to nonmetals, and therefore they're considered molecules. And then we have formula units. A formula unit is a compound held together by an ionic bond. So that's a metal and a nonmetal. So here we have calcium chloride. You could have something like sodium chloride or iron carbonate, something like that. A metal and a nonmetal. And so atoms, ions, molecules, and formula units are all considered particles. So 1 mole, if we're trying to quantify something really, really small like atoms, 1 mole helps us figure that out, because a mole is a measurable amount of atoms or ions or molecules or formula units, and it's 6.022 times 10 to the 23rd particles. That's how many I need of something before I can get something close to a measurable amount of stuff. It's a humongous number. So let's continue on with counting. If I have 1 dozen carbon atoms, how many carbon atoms do I have? Well, I'd have 12. A dozen is 12. If I have a couple of hydrogen, how many hydrogen atoms do I have? Well, I have 2 hydrogen atoms. Now, if I have 1 mole of copper, how many atoms or particles of copper do I have? Well, I would have 6.022 times 10 to the 23rd atoms or particles of copper. It's a humongous number of atoms, but if we think about how small they all are, how much they weigh, how little space they take up, and we realize that I really need that many to even know that it's really there. Another way of counting is, or making a measurement, is by using percentage. So if we look at a rescue shelter and we say that 10% of the animals at the rescue shelter are cats, well, we can ask how many cats are adopted in a group of 10 pets. So if I have 10 pets that get adopted, and we know that 10% of the animals at the rescue shelter are cats, how many cats got adopted? Well, 10% out of 10 would be 1 out of 10. So if I have 100 pets, how many cats are being adopted? Well, we know that cats make up 10% of the shelter, so we could assume that it's 1/10 of 100, or 10 out of 100. That would also give me 10%. And if I have 1,000 pets at the animal shelter, how many of them would be cats? Well, again, we could assume 10%. And so that would be 100 out of 1,000 pets would be cats. Now, percentages are nice because we can apply them to lots of different situations, either small numbers or large numbers. Then we have counting by mass. So if I go to the grocery store and I buy some bananas, and I tell you that the price is 59 cents per pound, and I want to know essentially how many bananas did I buy, I can tell you I paid $2.36 for these bananas. Now I could ask you, what's the weight of the bananas? I wouldn't exactly know how many bananas I bought because, well, bananas are different sizes. Some are smaller, some are bigger. And so it would be hard to tell you exactly how many there are, but it would kind of be hard to tell you exactly how many atoms there are if I try to count atoms this way, because we know that there are isotopes of atoms, and so some atoms have the same number of protons, which makes them the same kind of atoms, but they have different numbers of neutrons because they're isotopes. So I could have something like carbon-12 or carbon-13 or carbon-14, each with 6 protons, but maybe with different numbers of neutrons, and therefore different masses. Bananas are similar. They'll probably weigh roughly the same amount. They're similar sizes, but they're not exactly the same. So how could I figure this out? What's the weight of the bananas that I bought? Well, what I would do here is I would use a conversion factor. So what I could do is I could take these 59 cents per pound and use it as a conversion factor along with the money that I paid, the amount of money that I paid. And how would I figure that out? Well, is I could take the amount of money that I paid and use my 59 cents per pound as a conversion factor. And so what I could say is that for every 1 pound of bananas I buy, it'll cost me 59 cents. And if I do that, I can essentially cancel out the amount of dollars that I'm paying and end up with pounds. And so if I do this, I can find out that $2.36 divided by 59 cents and give me roughly 4 pounds of bananas. That's how many bananas I bought. I bought 4 pounds worth, whatever that is. So what we have here is a mole, and a mole is a way of kind of figuring out how many things I have. What's the amount of stuff that I have, and specifically how many atoms, ions, molecules, or formula units. The formal definition is the amount of a substance that contains the same number of fundamental particles or atoms as there are in exactly 12 grams of carbon-12. Carbon-12 is the mass number. It tells you how many protons and neutrons it has. Carbon usually has 6 protons, and in this case it's going to have 6 neutrons as well. And then again, fundamental particles here just are referring to particles, which which could be anything from atoms to ions to molecules to formula units. And again, these are examples of what those things are. And then we have a mole. A mole is 6.022 times 10 to the 23rd, or 6 with 23 zeros after it, particles of anything. So that means I could have a mole of donuts. I could have a mole of water. I could have a mole of dollars. I could have 6.022 times 10 to the 23rd particles of anything. Hopefully this helps.